Hello, game theorists. So, in this section, we'll look at a very important question. Do Nash equilibria exist in general? We're going to center our analysis around Nash equilibria, so we should be sure that they really do exist in general. So, the answer turns out to be yes. Nash equilibria do exist in almost all games. I won't go through the full proof because that gets rather advanced. However, I will show you the idea behind the proof since I find it to be one of the more beautiful mathematical ideas that I've seen. So, what is beauty in math? I often think of it as being when two apparently unrelated concepts end up being connected in some surprising way. So, here's how it works. So, in our first definition of a Nash equilibrium, we said Nash equilibrium is where no player can change their strategy and get a higher payoff. We also had the equivalent definition that all players are playing best responses to everyone else's strategies. So here's what we'll do with that. V is going to be a vector of strategies. So we'll have player 1 strategy, then we'll have player 2 strategy, if necessary, if the game is big enough, there could be a player 3, player 4, etc. Now I'll define B of V to be the best response to V. So in Nash Equilibrium is where all players are playing best responses. That means that the strategies you're playing, V, are the best responses to themselves. It means it's a vector V where B of V equals V. So can we always find some V such that this is true? It turns out that the answer is yes. And here's where we make this very unexpected connection. Let's say we have V over here, and then we have B of V up there. So this line over here, that's where B of V equals V. It's the 45-degree line. So the strategies have to be in some range. Let's say they're in here. Now the best responses to those strategies have to be in the same range. So my strategy could be, I can play either A or B. That could be a set of strategies. And the best responses to them are similarly going to be in some range. So what could B of V look like? Well, there's a lot of possibilities. Depends upon how the game is set up. But it turns out that no matter how I draw a line here, at some point that line's going to have to cross this. So I start over here, eventually got to cross over. Or if I start over there and try to avoid it, but I got to cross over at some point. So no matter what B of V looks like, there's going to be some V somewhere. Might be here, might be here, might be somewhere else where B of V equals V. But we just said a Nash equilibrium is where B of V equals V. So I find it very surprising that this graph like this, we're just drawing lines to see if they cross over this. That picture somehow relates to proving that Nash equilibria exist. A connection that was very unexpected. And the applications go further than that. In econ classes, we talk a lot about market equilibrium. Did you ever wonder, do we know for sure that market equilibria exist? Well, it turns out that a market equilibrium can be written as a game between consumers, firms, and a character we'll call the market agent. The market agent is the one who's setting price. And the Nash equilibrium of that game, you can show, is the market equilibrium. Because we know that Nash equilibrium exists because of this, that also means we know that market equilibria exist. So this idea has even further implications. So to give you a better idea of how these best responses work, I'll go through an example. So let's say player 1 can play H or L, and player 2 can play E or N. Let's say the payoffs are like this. So before we stack it up in a vector, it's easier to do it individually. Here's what I mean by that. So the best response of player 2 to H. So that means that if player 1 is playing H, what should player 2 do? Okay, so if player 1's playing H, player 2 is our column player. Column player's payoffs come second. They could play E and get 4, or they could play N and get 0. Well, 4 is better than 0, right? So I'd rather play E. So E is my best response. We'll write that like this. What is player 2's best response to L? Player 2's column player's payoffs come second. They care about these numbers if player 1's playing L. They could play N and get 0, or they could play E and get -1. Well, n's better, right? Better get 0 than get something negative. Let's do it for player 1. So if player 2 is picking E, then what should player 1 do? Player 1's payoffs come first, because player 1's our row player. If E is being played, we're in this column. So player 1 could play H and get 4, or play L and get -1. Getting 4 sounds better to me than -1, so that would be H. What's our best response to N if we're player 1? So N means we're in this column. Well, either way we get 10. So H or L. So you can see from our best response analysis, we have 2 Nash equilibria. We have HE, and we also have LN. Now let's go and write our best response vector. So I got the individual best responses, what this player should do in response to that. To finish the job, I got to stack it like this on this vector, so we have this B of V and V. So you got to be a little bit careful here. It looks straightforward at first. Player 1 on top, player 2 on the bottom. What could be easier? We got to be careful though is that what we're doing here is we have player 2's best response to player 1's strategy. So kind of going back and forth between player 2 and player 1 there. So some care is required. So the best response to HE, that's going to be player 1 is playing H, so we look at player 2's best response to H, that is E. Then we look at what is player 1's best response to E. Best response to E is H. Oh. You see what I mean about you have to be careful with this? I just switched things up. That should be H on top and then E. So what you're doing is doing the best response for player 1, player 2, and that is you're going to have best response from player 1 to P2 on top, and then you have best response to player 2 to P1 on the bottom. So this is a Nash equilibrium because you have best response to V is V. Okay, let's do another one, and I'll try not to get mixed up. Okay, let's do best response to LE. So player 1 plays L, and player 2 is playing E. So we gotta put player 1's best response to E on top. That's H. Player 1's best response to E is H. On the bottom, we put player 2's best response to player 1. So player 1's doing L over here, so we gotta find what is player 2's best response to L. Player 2's best response to L is N. So here, B of V does not equal V, so this is not a Nash equilibrium. Okay, another one. So I did HE already, and I did LE. So I've done these two. Let's do HN. So I got to do player 1's best response to player 2's strategy. Player 2's strategy is N. I'm trying to find player 1's best response to N. Player 1's best response to N could be H or it could be L. They're both equally good. So now I got to fill in this one down here. This down here is player 2's best response to player 1. Player 1's up there. Player 1's playing H. So what is player 2's best response to H? That was our very first one. We said player 2's best response to H is E. This is also not a Nash equilibrium because B of V does not equal V. I guess I could apply this to both, so I'll just erase that line there so you can see that. We have one last possibility. So I'm just missing LN, I believe. So let's follow our guide here and not get mixed up. So this means player 1 is playing L, and player 2 is playing N. We find over here player 1's best response to player 2's N. So what does player 1 want to do when player 2 is playing N? They want to play H or L. They're both equally good. All right, last part. So this is player 2's best response to what player 1 is doing. Player 1's doing that. That's going to be L in this case. So when player 1 plays L, what does player 2 want to do? They want to play N. So here we do have a Nash equilibrium because here B of V is V. So if you have multiple options here, it's okay as long as one of them has B of V equals V. It's still a Nash equilibrium. Now, this game here is actually not entirely novel to you guys. It's actually a rewritten version of the market entry game. You guys recall it from chapter 3? So in the market entry game, we had firm 2 could decide if they want to enter or not enter. So I'm calling not enter N, and I'm calling enter E. If they don't enter, then firm 1, player 1, gets the monopoly profits of 10. So payoffs are firm 1, firm 2. If they do enter, firm 1 then decides if they want to charge a low price, L, or a high price, N, H. So we said they charged a low price. That's going to drive them both into negative profits because they're just trying to undercut each other in price and drive the other firm out of business. If they charge the high price, then they both get profits of 4. So they're splitting up those profits. It's not quite as big, though, as the monopoly profits. Competition does drive down overall profitability. So this game here is equivalent to our market entry game. But in our market entry game, there is only one rollback equilibrium. We said that firm 1 should play H over here because they should get 4 instead of -1, which is better. Firm 2 knows they're going to play H. As a result, firm 2 feels free to enter because they know they can get profits of 4. That beats getting nothing. So we had two Nash Equilibria. Equilibria is the plural of equilibrium. We have two Nash Equilibria, but there's only one rollback equilibrium. That illustrates that Nash and rollback are not quite the same thing. We'll learn more about that distinction in future chapters. So that wraps up Chapter 4 on simultaneous move games. So be sure to join us in our next episode, in which we'll look at Chapter 5, looking at continuous strategies. In the meantime, stay safe out there.